Hey everybody, Mr. Covey here, and today we're going to be talking about a couple different things. If you could be on page 11 and 12 in your note packet, but you're probably also going to need another sheet of paper because we have a lot to talk about in this video, okay? As I like to say, we're going to put the B in BC in this video. You like it? All right, so first just a couple things to get our mind working. I got them on page 11 here. It gives us an infinite series here. The question asks us to write it in summation notation and then see if you can actually figure out what that series converges to, or if it converges. Okay, so as a reminder, summation notation, also called sigma notation, got a big sigma there. If you're looking at this and trying to write the sigma notation, it's very similar to the process Mrs. Lemke outlined for doing this with sequences. You're trying to map like n equals 1, n equals 2, n equals 3, n equals 4 to those terms. Like how can you put in 3 and get out 3/8, put in 4 and get out 3/16? If you look at this, you might be able to kind of just figure that out. You're like, oh, the numerator is always 3. You could write this a few different ways. A sloppy way to write it would be like, numerator is always 3, the denominator is powers of 2, and oh, it's just like 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, so I'll just write it like that. Starting with n equals 1 and going up to infinity. Okay. There's probably some of you sitting there going, wait, I'm writing a completely different thing. There's a ton of different ways to write it. Another way would be to look at this and just recognize it as geometric. It's a geometric series with a first term of 3/2 and a common ratio of 1/2. And if you did that, you might end up writing something that looks like this. First term times r to the n minus 1. Again, that might be a throwback to AATH, MAH. That's how you write a term of a geometric series, or sequence, rather. So again, if you plugged in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for r, these two things, the yellow and the blue, would give you out the same terms. Algebraically, you can rearrange them. It's the same thing. Okay. Writing it like this is probably beneficial just in the sense that you can tell it's geometric right away. And then if you actually want to answer the question, does the series converge or diverge? Oh, it's geometric with a common ratio of 1/2. Therefore, it's going to converge. What's it going to converge to? First term divided by 1 minus the common ratio. 3/2 divided by 1/2. That's 3. So yellow or blue is our sigma notation. What does it converge to? 3. Why don't you pause real quick and give 2 and 4 a try. And why don't you try to write it? Well, actually, write it however you want. You be you. Actually, pause the video. Pause the video. All right, friends. Actually, I don't know if we're friends yet. I don't know if I should say that. All right, everybody. No. Okay, so this is what I got for that first one. It was a geometric series. First term 1/2, common ratio -1/2. This is what I got from my sigma notation. I recognize it as geometric, so I use my geometric series formula, and I got that as sum to 2/9 because r is between -1 and 1. One thing I want to draw your attention to, again, there's lots of different ways to write this, is the fact that you're dictating or you're controlling what you start end with gives you some flexibility. It's common to start with 1. Sometimes people start with 0. If you start with 0, you can easily adjust this. It's just like, see how like I had an n minus 1 there, so when I plugged in 1, the first exponent was 0. Well, if I change it to start at 0, I still want the first exponent to be 0, so then I just shift everything. Because here I'm plugging in 0, 1, 2, 3, 4, 5 for n, and here I'm plugging in 1, 2, 3, 4, 5, 6 for n, so I just had to adjust that. Okay. So when you do sigma notation, you're allowed to change it. Both of these are equally correct, totally fine. Just make sure when you plug in when you plug in this, you get out the first term. Okay. Second one, geometric, common ratio -1/3, sum to 9/4. Okay. Moving forward. This is where you're going to want another sheet of paper. So far, when I've asked you the question, hey, does this series converge or diverge? This question, that's going to be a very common question in BC calculus. You've only been able to answer that question one way, and that is if the series happens to be a geometric, I'm sorry, I'm blank. then you can do what we just did. Check, you learned that in ATH, done. There are two other ways we're going to learn now to determine if a series converges or diverges. One of them is called the nth term test. One of them is called identifying a telescoping series. How many ways are there to determine whether a series converges or diverges? It's like 20 of them, straight up 20, no joke. We'll learn most of them, we'll learn the rest of them in the spring when we come back to series. But for now, we're just gonna stick to these three. So to talk about this nth term test, I want you to flip to page 12 in your packet and look at this sum. Half plus 2/3 plus 3/4 plus 4/5 plus 175, 6, 7, 8. And think about if that converges or diverges. Again, what we're talking about here is if you add up infinitely many terms, you're going to get a number, or is it going to get closer to infinity? Okay, put on your thinking cap. Thinking cap, use your brain. Okay, if you're using your brain, I hope you're like, obviously that diverges. These numbers are like really close to 1. Like you're going to get like 1,000 over 1,000, and you're adding a number really close to 1. If you do that infinitely many times, you're just going to get infinity. It's not like it's going to be like 28. It's not going to be a number. You keep adding and adding and adding a thing really close to 1, we're going to get close to infinity. I know this is a weird topic, but I hope you're developing that intuition. Okay. That's just a thought. There's actually like a reason to support that, a math idea that lets you conclude that, and that's called the nth term test. Okay. Okay. So if you have write this down. Okay. If you have a series that converges, obviously the associated sequence, those terms have to be approaching 0. Okay, I'll say that again. If you have an infinite series, and I should really write like a little infinity up there, infinite series, then the terms themselves have to be getting closer to 0. You cannot add up infinitely many things and get a number unless those things are getting closer to 0. Okay, and that's kind of the problem we're running into here. Is like these numbers aren't even getting closer to 0; they're getting closer to 1. So if you add up infinitely many of them, obviously you're just going to get infinity. So if it converges, then this is true. Because we know this fact, that's a fact, we know the contrapositive is also true. And a little PSGH throwback. I didn't teach any of you guys in PSGH. You're after my time, but those are the good old days. Mr. Wilhelm, great man, great man. The contrapositive of that's true. Remember, the contrapositive is where you flip the if and the then, and you give them both a not. So the contrapositive says, oh, if the limit of the sequence is not 0, well then of course the series diverges. Okay, I know this is tricky. I'll say it again. If the terms in the sequence aren't even approaching 0, if their limit's not 0, well then of course the series diverges. Okay, this is the nth term test. And it's officially called the nth term test. Me and Lemke like to call it the nth term test for series diverging. For a very specific reason, we like to add that little thing in there. We'll talk about it in a second. Okay. So if you go back to this problem we were doing here, let's write it in sigma notation real quick. Okay, again, I'm just going to kind of use my brain here. I'm trying to map 1, 2, 3, 4 to those terms. The numerator is just that. Denominator is one more. Here, I wrote it in sigma notation. Because the limit as n goes to infinity of the sequence, note I'm not writing the sigma here at all. Of the sequence, what's the limit as n goes to infinity of n divided by n plus 1? What's a million divided by a million plus 1? What's 10 trillion divided by 10 trillion? Is 1. Because the limit of the sequence is 1, the infinite series obviously diverges. Okay? The reason, the explanation for that is this nth term test. That is an official name. They will talk about it on the AP exam. you will say by the nth term test, or the nth term test for series divergence. This is the first time we are justifying that a series does not converge or diverge. That's not geometric. This one's not geometric, but by this nth term test, we can say it diverges. Okay. Cool. Pretty easy. If you have a series and the terms aren't approaching 0, well, then of course it diverges. That's called the nth term test. Okay. Pay very close attention here. You're going to make a mistake that everybody makes a ton of times. We call it the nth term test for series divergence because what does it do? Tells you whether a series diverges, tells you a series diverges. I almost caught myself there. That's all it does. Diverges. Does the series diverge? It can answer the question, yes. It does not tell you convergence. Okay. It does not tell you whether a series converges. So it's not like you're checking if the nth term test applies and then it tells you whether it converges or diverges. Either the nth term test applies and it diverges, or you know absolutely nothing. I will say that again. Either the nth term test to the series, for series divergence applies. Either you can use this test and you can determine that the series diverges, or nothing. You don't know anything. It doesn't tell you convergence. You're never going to say converges by the nth term test. Never. This is not a thing. It can't tell you that. That's not what it does. It tells you divergence or nothing. It doesn't tell you convergence. Okay. I will give you a counterexample to illustrate this point. Let's say you walk up to this series. You'll notice I talk about this series a lot because it's a great series, the harmonic series. 1 plus a half plus a third plus a fourth. And you look at this series and you're like, let me think about the nth term test. Well, the limit as n goes to infinity of these terms. Well, these terms are actually getting closer to 0. Oh, cool. The terms are getting closer to 0. So what do I know? Nothing. Nothing, 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 nothing. Don't try and act like just because the terms are getting closer to 0 that the series converges. People make this mistake all the time. You don't know anything. Can you use the nth term test in this problem? No, because the terms are in fact getting closer to 0. So move on. Can we tell if this converges or diverges? Right now we have no other method, but we cannot use the nth term test to tell us the series converges. In fact, this does diverge. The nth term test cannot help us here. You don't know that yet. We'll learn this later, but don't make this mistake of thinking that it tells you convergence. Okay? Never say this. Never, ever, ever. Don't say this. Don't say this. Don't say this. Cool. Here's a little Venn diagram I made. It might be more confusing than it needs to be, but I liked it. If you don't want to use it, you don't have to. What this says is, if your limit of your sequence is not 0, then you're in a divergent series, right? Like if your terms aren't even getting closer to 0, of course the series diverges. Okay. However, just because your terms are getting closer to 0 doesn't mean it's necessarily a convergent series. All convergent series have their terms getting closer to 0, but not all series with their terms getting closer to 0 are convergent. There's this sliver here. What lives here? What has terms getting closer to 0 but diverges? The thing we were just talking about is a great example. The terms are getting closer and closer to 0, yet it's divergent. So just be careful that that sliver in the middle exists. Okay, flip back to your packet, pause the video, just to give 9 and 10 a try. Again, the question is, does the series converge or diverge? And if it converges, what does it converge to? Give 9 and 10 a try. Okay, so for number 9, I looked at this infinite series in sigma notation, and I noticed that for the sequence, again, that's the sequence part, the limit as m1 to infinity of that was 3. In other words, the 10 millionth term is going to be really close to 3. Well, wait a second. If the terms aren't even getting closer to 0, then the series diverges, and that's the nth term test. Okay. For 10, there's 2 ways to do this. I just recognized that it was geometric and that the r wasn't between -1 and 1. So I know that geometric series with the r not between -1 and 1 diverge. Alternatively, you could use the nth term test idea here. But I think the better way to do this is to recognize this is geometric. Okay, cool. Notice that on my little flowchart here, or sorry, my little list here, I put nth term test first because it's kind of like the first thing you should check. If the terms aren't even approaching 0, then what are we doing? What are we doing, friends? Okay. Okay, now I'm going to talk about this last technique, which is called telescoping series. Again, you're going to just need a sheet of paper to write this down on. Okay, so let's say you walk into a series that looks like this. This is a little different than any series we've seen so far. If you're looking at a series and you're kind of like, that's weird, plug in 1, 2, 3, 4. Plug in some things to get a feel for. So I'm going to plug in 1. I'm going to plug in 2. I'm going to plug in 3. Plug in 4. And again, I'm adding all these guys together. Whatever. And if you look at this, you might look at this and go, wait a second. I remember math. A bunch of stuff's canceling out. I got a minus a half and a plus a half, and a minus a third and a plus a third, and a minus a fourth and a plus a fifth. I got a minus a fifth here, and now a plus a fifth. Infinitely many things are going to cancel out forever and ever and ever and ever. What am I left with? Just the first thing, 1. Sweet, that's my answer. That's so easy. Why is it called telescoping? You guys know like telescopes, like pirates use. They like close in on each other, like because they like overlap and everything cancels out so that you're just left with like a little piece of it. It's kind of like what happens here. A bunch of stuff like overlaps and cancels out. So this is easy. If you come across a telescoping series, sweet. Okay, going back here, there's not really a lot to write about telescoping series. If you have one, sweet. Figure out what cancels the infinitely many things and see what's left. Now there's a little caveat to this, as always, which is you put on your little thinking cap and you're really thinking hard, you might have this question. Telescoping series are totes easy. I wonder if I can take a series or take series that don't look telescoping, they don't have this kind of format, and make them telescoping algebraically, right? Like they don't look like something minus something where you can tell stuff's going to cancel, but maybe algebraically I can manipulate them to make them look like this. And in fact, you can. Good question. And we shall do it now. Jump back to your packet on page 12, go to problem 13. If you walk up to this problem and you plug in 1, and you plug in 2, and you plug in 3, I think I'm doing this right. No, I did that one wrong. It should be 6. The point is, you get a series here. This doesn't look telescoping. Nothing's like canceling out. And you can tell by this format that it's not, doesn't appear telescoping. But using fancy math, we can make this into a telescoping format where a bunch of stuff's going to cancel out. And to do that, we need to use a algebraic technique called partial fraction decomposition. I'll say that again. Partial fraction decomposition. I'll write it out here for you. I think Mrs. Lemke just calls it partial fraction decomposition, but I call it partial fraction decomposition. So here's how it works. Please pay attention. This is kind of like a procedure that you need to know how to do. So again, our goal is to take this series that looks like this and make it into a way where a bunch of stuff's going to infinitely cancel. Here's how you do it. First off, you recognize that the denominator can be factored into those two factors. And what we really want to do is split it up into 2 different fractions. Okay, because you notice the ones that telescope, they're going to be like 2 fractions so that like stuff's cancel. Okay, and the denominator of the fractions are back. The denominators of the fractions are going to be the 2 factors. And what we want to figure out is what numerators, what numbers to put on the top so that these things are algebraically equivalent. These are equivalent. So we want to figure out, like, should A be 6 and B be 2, or like what A and B should be so that those things are equivalent so we can replace it. The way to do that is to do a weird algebraic process. Please pay attention here. First, I'm going to multiply through both sides, the entire thing, by n times n plus 1. Okay. So what I'm going to get on the left is just 1. The n's going to cancel, so I'm just going to have a times n plus 1, and I'm going to have b times n. Okay, so far so good. Again, I'm trying to figure out a and b. Here's the weird part. This isn't like weird algebra, at least to me it was. Let's get rid of one of these variables by picking a specific n value. So if I want to get rid of the a, then I want n plus 1 to be 0, because that would get rid of the a term. So I would let my n equal -1. So if n was -1, then this would be a times 0 plus b times -1. That would go away. I get negative b equals 1. I'd get b equals -1. I just figured out what b is. Okay, I know that's kind of a weird process. That's the way you do it. This is not something that there's a deeper understanding of. So don't ask me like why partial fraction decomposition works. I'll just say it kind of works. What does it have to do with? It has to do with finding a common denominator backwards, is essentially what it is. There's no deeper understanding. Just understand. Just be able to do this. Okay, going back here. That's how I figured out what b was. To figure out what a was, I want the b to go away. So what do I want the n to be? Well, I want the n to be 0. If the n is 0, then the b goes away. And I get 1a equals 1. In other words, a is 1. Through this little procedure, I figured out what a and b are. Again, what are a and b? They're the numbers to put here and here in order to take this non-partial or non-telescoping looking term and make it look telescoping. Okay, so I'm going to take this series here, and through this process called partial fraction decomposition, I'm going to take this and I'm going to rewrite it like with it a1, b -1. So I'm going to rewrite it like this. How can I do that? How am I allowed to do that? Because algebraically, these two things are equivalent. And that's what that partial fraction decomposition helped me determine. Okay? So now that the red is equivalent to the green, why is the green preferable? Well, because when I plug in 1, plug in 2, plug in 3, this is actually the series we talked about before. Jump over there. That's actually that series. So by rewriting it like this, I could figure out that it summed to 1 versus how it was originally written. When I had like whatever 1/2 plus 1/6 plus 1, I couldn't tell that. Okay, so I rewrote it as telescoping, and I could do what I did on the other slide and figure out that the series converges to 1. Cool. Okay. I want you to pause, and I want you to try number 14 on your own. Try and go through this partial fraction decomposition process. Okay, thanks for sticking with me. I know this has been a lot in the video. So you came up to this series, and if you plugged in 1, 2, 3, 4, 5, it would just look like a bunch of numbers. Nothing would be canceling out, and that's because it's not written as a telescoping series. Okay, if we want it telescoping, we're gonna have to split it up into 2 fractions. Okay, so here's me splitting it up. Here's me going through that partial fraction decomposition to figure out exactly what fractions I should split it into algebraically. Okay, so I multiplied through by the denominator. Here, I'm going to let n equals -1 to figure out b, because that's going to make the a go away. And I figured out that the b was 1/2. Alternatively, additionally, I let n equal -3 to get rid of the b to help me figure out the a. So you do both of these two things, one time to figure out the b, one time to figure out the a. So I got b was 1/2 and a was -1/2. Going back to the original problem, what that let me do was rewrite this series that I could do nothing with, like this. And now, I got the 2 terms added together, one of them is negative. This is starting to look like it might be telescoping, like it might have infinitely many things cancel out down the road. in order to actually determine if that is the case, I need to write out the first term, second term, third term, and sometimes you need to write out a lot of terms. In this case, I wrote out the first 5 terms. Again, all I did was plug in n equals 1, 2, 3, 4, 5, and I got these fractions. So the example I showed you before was the simplest example where like the things right next to each other cancel out. Here, infinitely many things are canceling out. You just got to be a little careful. All right, well, I got a negative 1/8 there being canceled by a positive 1/8. And the negative 1/10 and the positive 1/10 and the negative 1/12 and the positive 1/12. And this negative 1/14 is probably going to be canceled by positive 1/14 out there, and the negative 1/16 by negative or positive 1/16 down there. So a lot of stuff's canceling out, which is good. In fact, infinitely many things are canceling out. Notice in these last few, like everything is canceling out. That's great. Infinitely many things are canceling out, leaving me with a finite number of things. In fact, what I'm left with is this 1/6 and this 1/4. Okay, so that's my answer. What does that series converge to? 1/6 plus 1/4, which is 5/12. So that's what this series, my answer to the original question would be, does it converge or diverge? It converges to 5/12. Why? Because it's a telescoping series, and I made it look telescoping by doing that partial fraction decomposition and then plugging in and seeing infinitely many things cancel. Okay. I know this has been a lot. Just to jump back to our chart here. So here are ways to determine whether a series converges or diverges. Check for that nth term testing. Maybe the series is geometric, in which case I can use stuff from AATA. Or it either looks telescoping, or I can make it telescoping using that partial fraction decomposition. How do you know when you can use that partial fraction decomposition? Well, the one thing you'll notice is the denominator has to be factorable. It's not always going to work when the denominator is factorable, but that's a requirement. If you can't factor the denominator, then there's no way you can split it up like this. Okay. All right. Thanks for watching, guys. That concludes this video. Don't worry. We're going to practice this tons.